derivatives affect the shape of a graph. Now, we've already talked a little bit about the idea that if you know where your function is increasing, then you know your slopes in that region are all going to be positive. Like if I go through on an increasing function or a piece of a function where it's increasing and I draw slopes, I draw tangent lines, the slopes of those tangent lines are all going to be positive, right? So we had already made the analogy then that the derivative would be positive there. Anywhere the original function was increasing, the derivative was positive. Similarly, anywhere the original function was decreasing, if I drew tangent lines in there, every one of them would have a negative slope. So anywhere that I had a decreasing piece of my function, the derivative there would be negative. So we can also use that in reverse, right? Like the converse of that idea. And that is anywhere I can figure out where my derivative is positive, that would be where the original function is increasing. And where the derivative is negative, the original function would be decreasing. Because let's say they give me something like example number 1 where we've got this quartic function and they say, tell me where this function is increasing and decreasing without a graphing calculator. If I'm going to go through and solve that thing, like define my x-intercepts and then plot points and that type of thing, I could try to factor it by grouping. It doesn't factor by grouping. I literally would have to go back to P over Q. Remember all the possible values of the constant over all the possible values of the leading coefficient, and you try them till you find one that works, and you do synthetic division or, to try and break it. Oh, that's just a mess, right? But if I take the derivative of a quartic, I get a cubic. And it would be a whole lot easier to work with a cubic than it would a quartic. So that's where this is going to help me. Even though this is something that I already know, where the original function is increasing, the derivative is positive. If I think of that in reverse, where the derivative is positive, my original function is increasing, sometimes I can use the derivative to tell me things about my original function. And so that's what we're going to do right here. So if I take the derivative and I go through and I figure out where it's positive and negative, I'll know where that function was increasing and decreasing. So I don't actually need a graph of the whole derivative, right? Like all I need to know is where it's positive and negative. So all I need is a sine graph. So to make a sine graph, I'm going to remember set this equal to 0 to get my critical numbers. So let's go through and set this equal to 0 and solve it to get my critical numbers. So anytime I'm solving where I'm factoring, I'm always going to start with taking out the greatest common factor. And then what I'm left with is just a quadratic. In this case, it'll factor, but if it wouldn't factor, I could do quadratic formula. So what is this factor to be? So I'm going to get x equals 0, x equals 2, and x equals -1 for my solutions. So I'm going to come over and I'm going to start a sine graph with those critical numbers at -1, 0, and +2. Now, we're going to do a lot in this section and in subsequent sections of comparing two things, like comparing the derivative with the original or the second derivative with the first derivative or something like that. And so it's a really, really, really good practice to get into the habit of labeling your sine graph, because if we're comparing two of them, it's really helpful to the AP grader, to your teacher, and even to you to be able to see what you were looking at and what you were referring to. Okay, so label your sine graphs. All right, so once I've got my critical numbers on there, I need to figure out where this is positive or negative. I'm going to pick a test point, right? Can't use 0 because it's already one of the critical numbers, so I'm just going to use +1. If I'm trying to make a sine graph for the first derivative, when I take this +1 right here and I plug it in to see whether it's positive or negative, what do I plug it into? The original function or the derivative? I'm looking for the sine graph of the derivative. That means I want to know where the derivative is positive and negative, right? So when I pick that test point of +1, I have got to plug that +1 into the derivative if I want to know where the derivative is positive and negative. And that's an easy mistake to make where I want to go back to the original function instead out of habit. If I'm building a sine graph for the first derivative, and I'm trying to figure out where the first derivative is positive and negative, I'm going to plug that critical number or that test point or whatever it is I'm working with, I'm going to plug that into the first derivative to figure out where the first derivative is positive and negative, right? Okay, so we're going to take positive 1 and plug it into the derivative, so that'd be 12 minus 12 minus 24. So I'm going to get a negative value. Doesn't even matter what the number is, just that it's negative, right? So over here at positive 1, I got negative. What happens when I cross a single critical number? Sign changes, right. We stress single critical number because if it is a double critical number, or it behaves differently, right? We'll deal with that in a few minutes. So now I've got my sine graph. We have been doing that since Algebra 2. We have done it repeatedly already this year, but it has been a little while since we've done that this year, so good review for us of how to create that sine graph. So now I can go through and say, okay, wherever my derivative was positive, my original function is increasing. Wherever my derivative was negative, my original function was decreasing. So I can come down here and say derivative negative, original function decreasing. Derivative positive, original function increasing. Derivative negative, original function decreasing. Derivative positive, original function increasing. And so I have that side-by-side comparison to be able to see what's happening. Now, if you think about it, if my function changed from decreasing, going down, to increasing, coming up, it went from going down to coming up, what would happen at that point where it changed? What would I have at the point where it changed from decreasing to increasing? I would have a horizontal tangent line, absolutely. And what would that value be? It would be a minimum. If you think about it, if my graph was going down, it was decreasing, and then it turns around and comes back up to increasing, at that point where it changed, isn't that going to be a relative minimum? All right, so what about if my graph changed from increasing going up to decreasing going down? What's going to happen at that point? A maximum, right. So I could again say, okay, right here it was decreasing, and then it switches to increasing, so what happens there? So if it changed from decreasing to increasing, then I'd have a minimum there, right? So we just kind of figured that out with logic and common sense. We just discovered the first derivative test. So they tell me over on page 241 that if your derivative changes from positive to negative, that would mean that your original function changed from increasing to decreasing, right? You're going to have a maximum there. So anywhere my original function changes from going up to going down, increasing to decreasing, that's where the derivative changes from positive to negative, there's going to be a maximum there. Anywhere your derivative changes from negative to positive, that would be where your original function changed from going down to going up. There would be a minimum value there, right? So where your derivative changes from negative to positive, you're going to have a minimum there. You might remember back when we talked about Fermat's theorem back in section 4.1, and we talked about critical numbers, and we said, okay, you find a critical number by setting your derivative equal to 0 or by looking at where your derivative doesn't exist. And we said, if you have a local maximum or minimum, it will occur at a critical number. But the converse of that was not true. Just because you had a critical number, that did not mean there had to be a maximum or minimum there. And so it was such a pain because the only way to figure that out was we had to go look at a graph to see, was there a maximum or minimum there or not. I don't have to do that anymore. Now I have a test that will tell me whether my critical number is a maximum or minimum or not. That's what the first derivative test does for me. I can do this completely algebraically now and not have to graph it at all and not have to look at a graph at all to be able to figure out my maximums and minimums, to be able to figure out if that critical number is a maximum or minimum or neither. All right. So if we go back to that problem that we just had, let's figure out where our maximum would be. The maximum is where we changed from positive to negative. So you can see that right here, the derivative changed from positive to negative at 0. So I'm going to have a maximum at 0. When I am looking for a maximum or a minimum, that's the maximum or the minimum of what? The original function, the derivative, the what? The original function. So if I have the x value of the maximum and I want to know its y value, it is the maximum of the original function. I plug back into the original function. So stressing that because a few moments ago we were talking about I didn't plug this one back into the original function, I plugged it back into the derivative. So we don't want to accidentally take the 0 and plug it back into the derivative. We want to plug it into the original function. Okay, great. How am I supposed to know which one to use? When I'm trying to make a sine graph for the first derivative, where I'm trying to figure out where the first derivative is positive and negative, and I use a test point to figure out where the first derivative is positive and negative, I got to plug that test point into the first derivative, right? But if I'm looking for a maximum or minimum of the original function, once I locate its x value and I'm trying to figure out what the actual y maximum, y minimum would be, I got to go back to the original function for that because it's a maximum or minimum of the original function. So I plug back into the original. All right. For the minimum is where it changes from negative to positive. So, okay, we changed from negative to positive right here at -1. And we also changed from negative to positive right here at +2. So I'm going to have 2 of those. And sure enough, if I look at that graph over on the top of page 241, it has a relative minimum at -1, a relative maximum at 0, and a relative minimum at +2. But I didn't have to do any graphing at all. I can figure that out completely algebraically. All right, let's do another one of those. Example number 3. They give me a trig function on the interval from 0 to 2 pi, and they ask me to tell where that function, they actually could ask me several things. They could ask me where the original function is increasing and decreasing, or they could ask me where I have maximums and minimums, and I would do the same work either way, right? So in this case, they asked me for maximums and minimums. So I'm going to go through, and again, I'm going to set the derivative equal to 0. So derivative of x is 1, derivative of 2 sine is 2 cosine. How do I solve that? Subtract 1, divide by 2. Perfect. So I need a reference angle. Where's cosine equal to 1/2? Pi over 3. And then cosine's negative in the second and the third, right? So I'm going to give the second quadrant pi over 3, which is 2 pi over 3. And I'm going to give the third quadrant pi over 3, which is 4 pi over 3, right? So those are going to be my 2 critical numbers. I also need to check and make sure there's nowhere that the derivative doesn't exist, like 0 in the denominator or negative under an even indexed radical. I don't have any of that here. I have a trig function. Trig functions are continuous or differentiable for all values in their domain, and this domain is all real numbers, so I'm good. Those are my only 2 critical numbers. So I'm going to come over and make a sine graph. I'm going to label it that it's for the first derivative. And so I've got those 2 critical numbers. Each of them is a single critical number. I got that answer just one time for each of them. So let's pick a test point. I'm going to use 0. And I'm trying to create the sine graph for the derivative here. So I'm going to use a test point of 0. What do I plug that into? The derivative, right. I'm trying to figure out where the derivative is positive and negative. So when I get that test point, I plug it into the derivative. So if I take 0 and I plug it into my derivative, that would be 1 plus 2 cosine 0. So 1 plus 2, the cosine at 0 is 1. So 2 times 1 is 2 plus 1 gives us positive 3. I don't really care what the number is, really just that it's positive. So positive here. Cross a single critical number, what happens? Sign changes. And then cross a single critical number, sign changes again. So there's my sine graph. I very easily then could say the original function was increasing here, decreasing here, increasing here. They didn't ask me for that. But I do know that where the original function changed from increasing to decreasing, it changed from going up to going down, that'd have to be a maximum there. And that's what my first derivative test said as well, that anywhere my derivative changed from positive to negative, I would have a maximum. Anywhere my original function changed from decreasing to increasing, going down to going back up, there'd have to be a minimum there. And that's what the first derivative test said as well, where the derivative changed from negative to positive, there'd have to be a minimum there. So I'm going to have a maximum at 2 pi over 3, and I'm going to have a minimum at 4 pi over 3. So once I get 2 pi over 3, what do I plug that back into? The original or the derivative? The original, because I am looking for the maximum or the minimum of the original function. So I'm going to take that 2 pi over 3 and plug it back into the original function. So 2 pi over 3 plus 2 times the sine of 2 pi over 3. So 2 pi over 3 plus 2 times the sine. The sine value there is square root of 3 over 2. So multiply that by 2 and we just get square root of 3. All right, we said our minimum would be over here at 4 pi over 3, so same story. Let's take 4 pi over 3 and plug that back into the original function. So we'll get 4 pi over 3 plus 2 times the sine of 4 pi over 3. Sine at 4 pi over 3 is negative square root of 3 over 2. So if I multiply that by 2, I just get negative square root of 3. Back when we worked with Fermat's theorem, we ran into a problem that was troublesome to us, and that was y equals x cubed. The problem with y equals x cubed was when we took the derivative and set it equal to 0, we got a critical number at 0, but there was no maximum or minimum there. So we've talked about how we can use the first derivative test to figure out where I have local maximums and minimums. But the first derivative test has a third part to it that'll help us figure out whether those critical numbers are maximums and minimums or not. We haven't had a way to do that. We've had to graph the thing to figure that out. So let's go back to that discussion that we had on y equals x cubed in light of critical numbers in Fermat's theorem. The third part of the first derivative test says this: if your derivative does not change signs at your critical number, then there's not a local maximum or minimum there. If it changes from positive to negative or negative to positive, yes, you have a local maximum or minimum. You have a relative maximum or minimum. You have a local extrema or a relative extrema. But if the sign does not change at that critical number, then you do not have a maximum or minimum there. So look at how that fixes the problem that we had back in 4.1. When we had y equals x cubed, we went through and we took the derivative and set it equal to 0, and we got a critical number at 0, but we didn't have a maximum or minimum there. And we said, how are we supposed to know that other than graphing the thing? We're trying to avoid graphing the thing. Now we have an algebraic way to fix that. Because if I were to make that sine graph for that first derivative and say, okay, there's a double root right there, if I picked a test point, like let's say that I plugged in a positive 1, and I got a positive value, what happens at a double root? The sign changes twice, right? So it looks like it doesn't change at all, right? If I had picked a test point on the other side over here, it also would have been positive. So that's why I wasn't getting a maximum or minimum at x cubed. The entire function is increasing. The whole thing's positive. There's nowhere that the cubic function switches from increasing down to decreasing or decreasing back to increasing. It's just that continuous curve where the whole thing is increasing. Before, I had to look at a graph to figure that out. Now I can use the first derivative test to say, okay, if there's no sign change, then there's no relative extrema. I don't have to graph the thing anymore to figure it out. So we focus primarily on the first and the second part of the first derivative test, and people tend to overlook that third part. But that third part is really helpful in helping us resolve an issue that we didn't have a way to fix before. And so you can see how that can help us. All right, the same way that the first derivative can tell us things about our function, the second derivative can also help us with some things about our function. The second derivative can tell me where my graph is concave upward and concave downward. All right, concave upward is basically something that kind of looks like a cup, and concave downward is kind of something that looks like a cap, like a ball cap. So over on page 243, they tell me anywhere that your second derivative is positive, your function is going to be concave upward. Anywhere your second derivative is negative, your function is going to be concave downward. So I'm going to do the exact same thing with the second derivative that I did with the first. I don't need the whole graph of it. I just need a sine graph. I just need to know where it's positive and negative, right? So I'm going to go through, and first I'm going to find my second derivative. All right, so what's my first derivative? And so then what's my second derivative? 6x minus 2. All right, so I'm going to set that equal to 0 to find the critical numbers for my sine graph. So I'll get x equals 1/3. And there's nowhere that that second derivative doesn't exist, that it's not differentiable, so no other value that I'm going to have to plot on that sine graph. And again, I'm labeling this just to make it clear to myself, but also to the grader, what it is they're looking at. Okay, so I'm going to pick a test point because I need to figure out where the second derivative is positive and negative, right? So I'm going to pick a test point. I'm going to use 0. What am I going to plug 0 into? The second derivative, yes. So I'll take 0 and plug it into the second derivative, and I'll get 0 minus 2. So negative 2. Doesn't really matter what the value is, primarily that it's negative is what we're interested in. And then what happens at a single root? Sign changes. I only got 1/3 one time, so the sign is going to change there. So I can look at that then and I can say, okay, that tells me that my original function is concave downward here, and my original function is concave upward here. Because anywhere the second derivative is negative, the original function is concave down. Anywhere the second derivative is positive, the original function is concave up. If they wanted me to give that as intervals, I could. And you'll notice that when I give those intervals, I'm using a parenthesis for 1/3. I'm not using a bracket. The reasoning there is if I put a bracket with the 1/3, I'd be saying that 1/3 is concave up and concave down at the same time. How is that possible? It cannot be two different things at the same time. In fact, it's not either. It is the one point where my function changed from concave downward to concave upward. And that is called a point of inflection. The point of inflection is the point where your curve changes from concave upward to concave downward, or vice versa. So like we were talking about y equals x cubed a little bit ago, and we've got it graphed up here. If you'll notice, this piece from negative infinity to 0 is concave downward, and this piece from 0 to infinity is concave upward. So 0 right there would be a point of inflection where it changed from concave down to concave up. In our example right here, 1/3 would be our point of inflection where our function changed from concave down to concave up. So they're going to want the whole point of inflection, not just the x value. So if I know that x is equal to 1/3, how do I find the y value? Plug back into the original, the first derivative, the second derivative, what? The original, right. The point of inflection is the point on the original function where it changed from concave upward to downward or concave downward to upward. So if it's on the original function, I need to plug back into the original function. So that would be my point of inflection.